name is Vinod Kumar, and today in this video we are going to study about electric field due to a uniformly charged infinitely long wire. Let us say we have a wire, infinitely long wire, such a way that the plus Q charge is placed here, and this wire is infinitely long. The wire is infinitely long, and as we can see that this wire is, we can say, uniformly charged, and its linear charge density is lambda. Let us say the lambda is the linear charge density. Linear charge density. Linear charge density of the given wire. So let us say that the total charge of this wire, is capital Q. The total charge of this wire is capital Q. So there are, we can say, many methods to find out the electric field due to this uniformly charged straight wire. But in this case, we are going to study the electric field, we can say the application of Gauss law, in which we find the electric field of the symmetrical objects. So this, we can say, the wire is, we can say, it is a symmetrical object in which the plus charge is accumulated. Now let us assume a Gaussian surface, or we can say, let us say we want to find out the electric field at some distance r from this the distance r from this uniformly charged electric wire. Okay, so now let us assume that there is a Gaussian surface, and that Gaussian surface is of the shape of cylinder. Okay, so we are going to draw a cylinder of radius r, such that it forms a Gaussian surface. Okay, so this is the, we can say, cylindrical surface or Gaussian surface which we have drawn, and now we are going to find out the electric field due to it. As we know that according to Gauss law, the electric field is, according to Gauss law, the electric field will be the closed integral over E vector dot ds vector equals to Q enclosed divided by epsilon naught. Here we are taking epsilon naught because we are assuming that there is a vacuum, the case of vacuum, and here the Q enclosed is the charge enclosed in the closed Gaussian surface. So here we have assumed that the closed Gaussian surface is the cylindrical surface, and there are, we can say, in a cylindrical surface, there will cylindrical shape, or we can say cylindrical Gaussian surface, there will be three surfaces. Two surfaces are, we can say, the circular surface, and the one surface is this one, the curved surface of a cylinder. This will be, there will be three surfaces. So let us name them. That the first surface is this one, and the area vector due to this surface will be pointing outward, or we can say nk, and for due to this surface the area vector will be pointing outward. And as we know that the electric field due to a positive charge always points towards, we can say, in the outward direction. So the electric field will be due to this we can say the horizontal line of the charge. The electric field will be pointing in this direction because it is the, we can say, radially outward direction. Okay, now let us name them. This surface is first surface. This, again, the circular surface of this right side is it is named as 2, and this curved surface is named as 3. Now we are going to we can say expand this integration into three parts. Okay, so now it will be E vector dot ds vector for first surface. This is for first surface plus E vector dot ds vector for second surface plus E vector dot ds vector for third surface. Now on the equal side it is Q enclosed divided by epsilon naught. So we have divided this integration, or we can say the closed surface integration, into three parts. First for this surface, second for this surface, and third for this curved surface. Okay, so now let us know the angle between, since it is a dot product, E vector dot ds vector, then again it is here E vector dot ds vector, E vector dot ds vector. So first of all we should know the angle between the electric field vector and the area vector. So for this first surface, the angle between for the first surface, the angle between the area vector, this n cap is the direction of area vector of this circular surface, that will be in the leftward direction. And as you know that the direction of the electric field is upward, so this will be the direction of electric field, and as we can see, the angle between area vector and the angle between area vector and this electric field vector is 90 degree. In this case it is 90 degree. And for the second surface, similarly, the angle between the area vector and electric field vector will be 90 degree. And for this case, for this particular case, or we can say in this the third surface, which is the curved surface, the angle between area vector, since it is the curved surface, so as you know that for the curved surface, the area vector will point out, we can say normal to the surface. So it will be along with the electric field. So it at this point P, this will be the direction of the area vector, and we can say that in this case the direction, the angle between area vector and the electric field vector is 0. It is 0 degree. Okay. So now for first surface, let us write for first surface it is E ds cos 90 degree plus for second surface it is E into ds cos 90 degree plus third is E dot ds into cos 0 degree. Okay, the angle between the area vector and the electric field is 0 degree. Now it will be equivalent to Q enclosed upon epsilon naught. Now as we know that the value of cos 90 is 0, and for this also the cos 90 will be 0, and the value of cos 0 degree is 1. So that is why this will be equivalent to 0, this will be equivalent to 0. Now it will give us E into ds equals to Q enclosed upon epsilon naught. Now as we can see that the electric field for this curved surface is equal for every point. Everywhere we can say the point which we are taking, the electric field is equal. So we can see that the electric field is constant, and it can be taken out of the integration, and it will be simply E into third surface integration of area vector equivalent to E enclosed upon epsilon naught. E enclosed upon epsilon naught. Now our task is to find out E enclosed. What is the charge enclosed in this Gaussian surface which we have made here? Okay. So the charge density is lambda, and if the length of this cylinder is L, then the enclosed charge will be here. Q enclosed, it will be lambda into L. The charge enclosed will be lambda into L, where lambda is the linear charge density of the given straight wire, which is infinitely long. Okay, the one word is coming here, that is infinitely long. Why do we call it infinitely long? Okay, so the distance r which we are taking, it should be very small with respect to the length of the wire. So we can say with respect to the length of the wire, we can say the point of interest that r is very small as compared to the length of the wire, and the length of the wire it can be taken as infinite. Fine. So Q enclosed we have find out here. Now let us place in the equation. So it will give us the result as for third surface E integration over ds equals to lambda into L upon epsilon naught. Now as we know that the integration of the area vector for the third surface, the area of the curved surface of a cylinder will be 2 pi r into L. So it will be E into 2 pi r into L equals to lambda L by epsilon naught. Now this L and L will be cancelled out, and we will get the equation as electric field E vector lambda upon 2 pi epsilon naught into R. 2 pi epsilon naught into R. This is the equation of electric field due to a, we can say, straight conductor wire on which the positive charge is placed, and where lambda is the linear charge density of the given wire. Okay. And now if we want to write in this the given the electric field in the vector form, so in vector form we can write it will be E vector equals to lambda upon 2 pi epsilon naught n k. And the n k which we are taking here, that is this n k, the area vector of the curved surface. This is what the electric field. And if we more precisely we call, if the unit vector n k is written by r k, we can say radially outward. The r k is the radially outward direction. It is a unit vector along this the radially outward direction. So this will become lambda upon 2 pi epsilon naught into r k. This is the desired electric field due to a straight conductor wire at a distance r. So that is how we can find out the electric field. I hope you got the idea. Thank you so much.